Okay, so we've got Worked Solution 17 to look at. So that's on page 202, and that's got a solid alloy shaft, 60 millimeters, is friction welded concentrically. So it's a bit like I've got a shaft with a hole in it, and then I've got this other section here where I've joined that section with this section. And friction welding means you spun them around so quickly they create a heat, and then let them cool down, they fuse together. It's in series. There's an end hollowed shaft which has the same external diameter as the solid shaft, and they are going to experience the same torque. Okay. The angle of twist per unit length of the steel shaft is 75% of the alloy shaft. So this is my alloy, this is my steel. And when the torque is being applied, there's going to be less twist of the steel than the alloy. So this per unit length. So if you measured the same amount of length there, this twists less by about a third. And the other condition that we got is that the modulus is a ratio of modulus of the rigidity, so it's torsion. It's like the Young's modulus for torsion, as a ratio of GS equals 2.2 GA. So the two conditions we got is that GS equals 2.2 GA, and the twist per unit length is 0.75 for the steel compared to the alloy. So these are the two conditions from the course notes, and everything else is there on that diagram. Okay. So the first thing is to show that the polar second moment of area for the alloy is 1.65 compared to that of the steel. So we're using the torsion engineer equations. So we're using the first column and the third column here. So that's torque divided by polar second moment of area equals the shear stress divided by R, where R will typically be the outer radius, some sort of radius, times by the modulus of torsion, angle of twist, divided by the length of the beam or rod that you're looking at. So we're going to use this and this bit. Notice that for torsion problems you tend to use this bit and this bit. For bending problems you tend to use this bit and this bit together. So what I'm going to do is write out my torsion equation for the first and third columns out twice. They're going to be valid for the alloy section and for the steel section. I know that the torque, because this is all one block that's been twisted, so I know that the torque is the same for both sections. So I can rewrite my equations so that we can get rid of the torque value. So TA is going to equal to TS. Then I can apply my condition, which was what, that GS equals 2.2 GA, and get rid of that. Okay, but before I do that, I'm going to go to the other condition, so the steel is twisting per unit length a bit less than the alloy. Okay, so let's go back to this equation here, and then let's pump in this condition. So we'll get rid of the steel twist and make everything in terms of the alloy twist. So the steel twist there divided by the length of the beam, we'll replace it with this condition here. So that means I can cancel out the twist and cancel out the length of the alloy. Now surely I'm going to apply the condition that GS equals 2.2 GA. Okay, so I note my condition from the question. Substitute in that GS equals 2.2 GA, so I've done that there. Now my GAs are going to cancel. And then we're left with 2.2 times by 0.75 for the polar second moment of area for the alloy compared to the polar second moment of area for the steel. 2.25 times by 0.75 equals 1.65. So we've shown that to be true. Calculate the internal diameter of the steel. There's probably various ways we can do this, so we're putting up the either condition. So we know that the polar second moment of area for the solid section here is going to be given as pi d to the power 4 divided by 32. Make sure you don't look up the correct term there. Don't get it confused with the second moment of area, which is pi d to the 4 over 64. Okay, so I and j aren't the same things. This is to do with bending stiffness, and this is to do with twisting stiffness. So I know my diameter, so I know what my GA is. So I've worked that out there. I've put my diameter in as meters, so my units coming out are going to be meters to the power 4. From my previous section, I know that there should be this relationship that GA equals 1.65 GS. So this tells me how much GS should equal. So GS should be the GA divided by the 1.65. So let's actually work out what the numbers are. We've got this number here. Now we can put in our formula for GS. So this is for a hollow section. So the big D is the outer diameter, and the little d is the inner diameter. So what I want to do is rearrange this to find my little d. So I can do that by first multiplying by the 32. 32 GS equals pi, multiply out the bracket, d to the 4 minus pi little d to the 4. So that becomes then pi little d to the 4 equals pi big D to the 4, take away 32 JS, and divide through by pi, so then I get d to the 4, little d to the 4 equals big D to the 4, we expect those units to be balanced, take away 32 GS divided by pi. So then I want to take it to the root 4, so I could use my root function on my calculator. So use that root symbol. So these numbers I should know. I know that the outer diameter, JS, I've just worked out, so I can just plug these values into my formula now. So plug them in. And now it tells me the diameter. Do a sanity check. Is D less than big D? And does it seem like a good, sensible ratio? So we're at 60. So I guess we're about 75%, I suppose, of 60, somewhere around that region. So it seems like a good, sensible value. So it's 47 millimeters multiplied by 1,000. Find out what it is in millimeters. So that's one way you can do it. Let's have a look at any alternatives. So another way is we'll go back to condition 1 again. And like before, we'll write out the formula for JA, write out the formula for JS, and we can now apply this and this into the condition that we previously found. So our pi's are going to cancel, our 32's are going to cancel. I suppose a bit more elegant solution here. Multiply out my bracket. Factorize there. The nice thing about this solution is that when we take the roots, d to the 4, take the root of that, and then the big D to the 4, they both drop down to become both D's. Okay, so d to the 4 equals this. Now, I would be tempted to have had that outside my root, so I would have said D equals 60 times 10 to the minus 3, and then in my calculator put those numbers. Well, okay, so in this presentation they've done it so that all the numbers go into the root 4, but it means then you have to raise this to the power 4, so a bit of redundancy there. So we're going to get the same result, multiply 5,000, so it's readable. The next part of the question is to find the maximum torque. So we were going back to the torsion equations, so let's recall what they are. Okay, so obviously you're going to be using the first column. Don't recall if we have values for G. Guess we do. Okay, this is been a while since. Let's have a look at the question again. So I can't see where it's saying anything. Okay. What is the maximum permissible torque in the alloy? We're not getting any additional information. Okay, let's see where the PowerPoint's going. So we're going to rewrite this in terms of the first and the second column. Now, where did the 50 times 10 to the 6 come from? Okay, so that was from page 204, and it says the limiting stresses for the alloy are 50 megapascals, and for the steel is 75 megapascals. Right, so you have to go back to the course notes and you'll see that we have a maximum shear stress of 50 megapascals for the alloy. So that's where that number there has come from. So that tells me that the maximum torque that can be applied in the alloy is 2,120 Newton meters. Doesn't sound like a big number, but that's actually a big number in terms of torque. For the steel, it has a maximum shear stress of 75 megapascals. Now, the maximum shear stress for metals tends to be about a third or so of the what's the other one I'm looking at? The maximum UTS or something, or yield or whatever, but they tend to be a smaller value. So UTS is probably going to be about 200 megapascals or so for steel, if not more. So I'm going to use my torque equation again, substitute in the 75 this time. The radius is the same, but I have to be a bit careful because my J will be different for that section. So rewrite this to find out what the maximum torque the steel can be applied. So we've got a different J value because this is a hollow section. So it's a different polar second moment of area compared to this, which is solid. The property of the steel has a different maximum shear stress value, but the outer radius is the same for both cases. So it turns out that the steel, although being a, if you like, stronger material, we have to apply a lower torque. So since this is a single shaft, the maximum stress we can load it to is going to be dependent upon the lower value and not the upper value. So that's going to be the maximum torque that we can apply before it breaks. So the maximum allowable torque is going to be that number there. So it's easy to fall into the trap of when we're looking for the maximum torque to think, okay, I want the biggest number. No, I want the smallest number that my components can cope with. Okay, that's the last work solution. I thought fanfares should go off or something.